All right. Good morning, everyone.
Hi.
Morning. Good morning. Apologies for the contrast. Would be great. So the projectors are in the back room here. They actually aren't out here in the room that you all are in. They're in the back room, and the lights are on in there. So I've already requested someone to turn it off. So hopefully, like somewhere in the middle of class, magically it'll become more clear. You can kind of see them, but I know the contrast isn't good since the lights are on in the back room. Whatever. Okay. Joke of the day. Iceland is only one sea away from Ireland.
Yeah.
It's like the letter C.
Oh my God.
Iceland. It's got a Ireland. You just change one letter, but it's also locationally only one geographic sea away from it. Great joke. See, they make you think. Okay. So, last class. Actually, before we do that, real quick. No, I'll do that on Monday. All right. Hey, look, it worked. Hey, what's up? Last class, we talked about Gauss's law. That's kind of, we did a continuous charge distribution, did some things with that. Try this out. There's 4 problems on the problem set. There's 1 on the quiz. Guaranteed to be 1 on the test. There's 1 on the recitation. Like, look, you need to know how to do it. Gauss's law came from this thing that I said last class, where Gauss said that if you draw a bubble around some charge, the number of field lines going through this bubble, we call this bubble the Gaussian surface, it's a fancy phrase for this, is proportional to the charge enclosed. So the amount of field lines that go through it, proportional means it's some multiple of the charge enclosed. And this is based on the idea, and this is not a shocking idea, it's just based on this. More charge, more field lines. Not a crazy idea. Now we need to express that in math, and this is where the disconnect might happen. How do we calculate in math the number of field lines going through an area? We introduced something called flux, which was EA cosine theta, and a bit more accurately, we might have to integrate that. Integrate that to get all the flux, because that shape is an area that's not a uniform vector. If the angle changes, if E changes, if anything changes, we need to integrate. That's why we do integrals, to add up the sum of things that change. This little circle around my integral just means it's a closed integral over the surface. I integrate over the whole surface. That's all that little circle represents. I'm doing it over the whole thing. It's like complete irrelevant. And then, of course, Q enclosed is epsilon naught. It's proportional to the charge enclosed. How is it proportional? Take the Q enclosed and multiply it by 1 over epsilon naught. Epsilon naught is a number. 8.854, and this is a typo, times 10 to the minus 12. It's a typo my next class recognized. On the formula sheet it was correct, but on here I accidentally put the wrong number. Okay, so this is Gauss's law, and the rest of this PowerPoint is me showing you how to use it. This is the entire kind of thing. So, let's go ahead and I'm going to write Gauss's law up here. What is the electric flux through the Gaussian surface shown in the image below? And I'm even going to write this equation for you, that electric flux equals the integral of E dot dA equals Q enclosed over epsilon naught. You have 2 ways to solve for flux. Pick the one that's reasonable. So, you get to watch me log in. Don't worry, my password's hidden, so all is well. Alright. Fingers crossed everything's plugged in right. Oh, and I did reset the iClicker points. I deleted all the old ones and made it only count from the days I said it would. So, at this point, it's accurate. At this point, the points that are there matter. The points moving forward matter. Okay, so is the electric flux 1Q over epsilon naught, 1Q, 2Q over epsilon naught, 2Q, or negative 1Q over epsilon naught? I'll give you all a whole minute on this. All right, y'all got about 20 more seconds. I know it's quick, but there's no math really required here. Calling it math is being very generous. All right, we'll close this out in 5, 4, 3, 2, 1. Okay, 2 ways to get flux. We could do an integral. This integral would require us to find the electric field every single place on this surface. I'd have to find the electric field here, and then I'd have to find it here, and then I'd have to find it here, and I'm just kind of approximating roughly what they look like. I don't even know what they look like. It'd be awful. Not only would I need to find the electric field at every single point, I would need to find the angle between it and the area vector at every single point. So at this point, you know the area vector is here. At this point, the area vector is here. At this point, the area vector is here. Hopefully, obviously, that's awful. Hopefully, you can recognize that is not what we're going to do. We are not, for this problem, going to do the left side, because that's awful. That's way too much work. What also equals the flux? Q enclosed over epsilon naught. So let's just figure out what's inside. What does Q enclosed mean? It means the charge, the total charge enclosed inside of that bubble I drew, that Gaussian surface. So how much charge is inside of this? We just count the charges. There's 4 positive, there's 2 negatives. So what's the total charge then? Q enclosed is going to be 4 minus 2. Or, if I want to write this maybe to make it more clear when you look at it later, 4 plus negative 2. And there's Q's. Each of these has a charge of Q, so 2Q over epsilon naught. Whatever each of those things are, they have some magnitude of Q. All right, great. There's the answer. The flux is proportional to the charge enclosed. So how much charge do I have enclosed? What's the proportionality constant? Epsilon naught. Make sure that's there as well. Don't forget about that. So great. Nice work. Nice work. Now, if you messed up, you probably just miscounted. That's really probably all that happened here. So the next couple questions are just more of the same. I'm not going to bother with them. Just more of the same. Really easy. Okay, so what's the point of Gauss's law? I've kind of built up Gauss's law. We've done flux in a conceptual way. We've done charge enclosed in a conceptual way. I've shown you the math. What's the point of all this? Why are we doing this? It lets us find electric field. That's the point. Gauss's law, let me actually even put that here. Lets us solve some problems. Specifically, Gauss's law lets us find electric field for some problems that would otherwise be pretty challenging. We're going to see some of those problems that if we try to do Coulomb's law with it, it'd be very unpleasant. It's a math trick in a lot of ways, but it's also a bit more comprehensive than Coulomb's law. We're going to actually use it to derive Coulomb's law at some point. Derive it. Just show that they're the same thing. And it's a bit more comprehensive. So it's a nice little thing. It is one of the 4 fundamental equations, though, that can explain all electricity and magnetism. So that's it's pretty useful. We're going to just use it for a few problems. But it's just more comprehensive than Coulomb's law. It's kind of another piece there. Okay, this next slide is going to have a bunch of things, and I'm actually going to break it into a few slides to give me space, because I realized when I taught in my last class I didn't have space. We, in this class, are only really going to use it for 3 types of problems. And I'm going to show you 3 geometries. 3 geometries. There's going to be a 1D case, a 2D case, and a 3D case. So this next slide is going to show that, and then I'm going to spend a decent amount of time explaining what the setup is, and why the setup is what it is. So here are the 3 scenarios. A line or rod of charge, we can use Coulomb's, we can use Gauss's law for that. A plane of charge, 2D plane of charge, so you have a piece of paper. And a sphere, or even a hollow sphere of charge. These are the 3 scenarios. A line, a plane, a sphere. But this like plane can be hollow. This line of charge can have some thickness to it. And so something that's going to be also here, you're like, we've done a line of charge before. What do we need this for? You're going to see it's way nicer using Gauss's law. But what Gauss's law lets us also do is find the electric field inside of the rod, if it's an insulator, which Coulomb's law would be very miserable to do. So we'll see some of those problems. Same with the sphere of charge. Outside the sphere, it's actually a trivial, so it's pretty simple. We're going to find it inside the sphere as well. The electric field inside the sphere if it was an insulator. So you'll be able to see that. And the plane of charge, we could probably do that with Coulomb's law, but we'd have to do a double integral. So again, this is just to make some things easier, and in some cases makes it actually possible. Okay, so here's 3 scenarios. I'm going to look at one at a time. One thing I want to point out before I begin, these dotted lines are the Gaussian surfaces that we're going to draw. Remember I kept mentioning these bubbles that we're going to put around things? We've had a bunch of problems. Here's this one. You had the bubble that was the red dotted line. Here's, so another bubble. When we did, where is it at? When we did this one in the first place, we had a bubble around it. You have to draw the right bubble, the right Gaussian surface around it. This is not a physical object that we're drawing here. It won't be shown in your picture. You have to pick the right shape, and you need to draw it. That's a really important skill that's going to come up here. And what is the right shape? That's what I'm going to spend the next time telling you all. These are the right shapes. So we're going to go through one at a time, and I'm going to explain why, and hopefully that's going to be useful. Yeah. So, boom, boom, boom. None of this is grouped together, so that's all right. So yeah, I could do it on here, but I realized it's not a good idea. It's way not enough space for me to draw what I need to draw. Okay, so here's my line of charge, and I don't like that I picked a negative charge, so we're just going to pretend this is a bunch of positive charges. I'm just going to draw over it, pretend like it's negative, like it's positive. This rod also needs to be straight up and down, but I didn't want to make I did not want to make one myself, so I was lazy and stole one from another place, from the OpenStax textbook. So, here's my rod. One day I'll be able to click the rod in it and make it straight up and down. You know what? I'm just going to make my own. All right, so here's a rod of charge. It's a line of charge with a bunch of positives. Positive, 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 positive. Doesn't matter if this rod has thickness or not. It could be it doesn't need to be infinitely thin. Doesn't matter. Here's the Gaussian surface I'm drawing around it. I'm drawing a cylinder around it. This cylinder is not actually there. This is a fake thing that we're drawing. Our goal is to find the electric field at point P. That's the reason this is like the setup for this problem. I have an infinite line of charge. Find the electric field at point P, some distance away from the rod. That's the question that we're solving. So we draw this Gaussian surface. We draw this Gaussian surface, the cylinder, and I'm going to explain to you why. This is the part that I want to try to convey. If you don't understand it, you'll be okay, but if you do understand it, everything's easier when you understand what and why. So we want to find E. We want to find E at this spot. What is E? That's the question. Gauss's law says this. This is Gauss's law. The integral of E dot dA equals Q enclosed over epsilon naught. That's Gauss's law. We're focusing on the left side right now. That's the side we're focusing on, this integral. If we can avoid doing an integral, we're going to avoid doing an integral. That's the idea here. We do not want to do an integral. If when doing Gauss's law, you are doing an integral, you are doing it wrong. That's the key kind of takeaway throughout this. So, how do we avoid this integral? How do we avoid this integral? I'm going to delete my shape here. We need to draw some shape, some bubble, such that I don't need to do an integral. How do I avoid doing this integral? We're going to focus on this side. E dot dA. So remember that this can be rewritten as the magnitude of E times the magnitude of dA times cosine theta. That's a dot product. Theta is the angle between E and the area vector. So, there's kind of three things we're looking for here. We need this angle to be a constant. If the angle is not a constant, I'm going to have to integrate. That's bad. I want the angle to be a constant. That's one rule. I want E to be a constant. If E is a constant and theta is a constant, what can I do? Pull them out. And then the integral of dA is just A. So it's not really an integral. I wouldn't call that an integral. So, we want this to be a constant. We want E to be a constant. We need to choose a shape to make that happen. And I'm just going to tell you all, that magical shape is the one that we saw before. It's a cylinder. And you all, this is a good exercise to learn how to draw cylinders. It seems stupid, but you just kind of draw a rectangle, and then at the top you put a little circle. How does a cylinder satisfy this requirement? First, we need to understand what the direction of the electric field is. If this is a bunch of positive charges, we've kind of already done this problem last class. The electric field at this point points to the right. Why does it point to the right? Because if I pick some little charge up here, it's going to point down to the right. If I pick a charge way down here, that's going to point up to the right. So, if I pick two charges on each side, what's going to happen to the up and down components? They cancel out. So it's going to always point to the right. That is true everywhere on this side. Everywhere on this side, and even everywhere on this side, the electric field points outwards. And it's the same value everywhere on it. How do I know it's the same value? It's an infinite rod. If you closed your eyes and I moved this rod down, you couldn't tell. It doesn't look any different. It's an infinite rod. There's no differences. So the electric field must be the same everywhere, because if you close your eyes and I moved it, if you can't tell that something's different, then it's not different. That's generally kind of a good rule of thumb. So, the electric field, yay, it's a constant. E is a constant everywhere on the side of that surface. Yay, that's good for us. Let's look at the area vector. Which way does the area vector point on everywhere on this surface? Outwards. So, the E is a constant. The area is a constant. So why is that good for us? It just becomes the integral of the side. Okay, so that's good on the sides. Remember I told you all this is a closed integral. I need the entire surface. A cylinder isn't just the sides. That's not a bubble. You can't have a bubble that's just a rolled up sheet of paper without a top and bottom. You need the tops and bottoms. So we need to consider the tops and the bottoms too. Let's look at the top and the bottom. If we look at the top and the bottom, which way does the electric field point? Still to the right, outwards. It points outwards. On this side it points outwards, on this side it points outwards. Points outwards. Which way does the area vector point on the top and the bottom? Up. Why is that good for us? What's the angle between the area vector and the electric field on the top? What's cosine of 90? So my integral turns to 0. So this is the magic here. Is the tops and the bottoms we don't care about. They're 0. We only care about the sides. So if we kind of write this, we're actually going to break it into two pieces. This is going to equal the integral of E times the area on the sides times the cosine of theta plus the integral of E times dA of the top and bottom. I'm just going to put both here. I don't want to write more than... We got to do the whole thing. So I break this into sides. I got the sides at the top and bottom. This angle is 90. So this term, gone. 0. Doesn't matter. This other side, theta is 0. E is a constant. So we can pull E out. And we just get the integral of dA sides. And the side of a cylinder, this is a really easy, it turns into the area of a cylinder. So you get E times area of sides of cylinder. And the sides of a cylinder are really simple. It's E times 2 pi RL. Where R is the distance from that to the point. L is the length of it. I know this is infinitely long. Don't worry about that for now. It cancels out later. So, this integral just becomes that. I had to do no integrals. This is the magic of choosing the right shape. We choose the right shape, so we don't have to do an integral. That's the punchline here. Okay? So now on the other shapes, I'm going to kind of go a little bit quicker. I'm going to show you the shape. I'm going to convince you very quickly that what the integral turns into, why we choose that shape, and then we'll start doing some problems with it. I know there's a lot of kind of mathematical stuff here, and that's why at the end of this is a nice summary slide pointing out the key things. So for now, I'm just trying to give you all a fighting chance of understanding why, but even if you don't, you can do these problems. You do need to know to choose a cylinder for a rod. Lock that in your way. If everything else didn't make sense, remember to draw a cylinder for a rod. That's the most important thing from this entire slide. Know that. Okay. We're now going to do a plane of charge. Fingers crossed everything's grouped there, but I'm sure it's not. Yeah, it's not. That's fine. I'll draw it myself. Here's a plane of charge. We're going to do the same thing. We're really just focusing on this left side. We're just focusing on this E.dA, so I'm not going to even write the right side for now because we're not going to bother with it. We will get to it when we solve problems. E.dA, we want the same thing. I do not want to do the integral. I do not want to do the integral. So, above this plane, we're trying to find E at some point above it. I don't, some random spot. I really don't care where. There's the point. The electric field here, which way is it going to point? I want you all to spend about 30 seconds to 40 seconds thinking. This is an infinite plane of charge. Infinite. This charge goes forever and ever in every single direction. Imagine an infinite sheet of paper. I want the electric field above it. It's positive. You all spend 30, 40 seconds, see if you can figure out the direction of the electric field at that point in your head. You can chat with people next to you too.
Yeah.
All right, the answer is straight up. Why is it straight up? If you picked a little charge over here, it's going to make a field to the right. If you pick a little charge over here, it's going to make a field to the left. Left and rights cancel. Symmetry, 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 symmetry. All right, so what shape are we going to choose here to make stuff either go away or be a constant? We are going to choose a cylinder that intersects it and goes through both sides. So it's very important that it goes through both sides, because if not, you're going to forget a term. A cylinder, and we're going to look at the sides of this. You know, how many sides are there in the cylinder? 3. Top, bottom, side. Three surfaces I can break this into. So we're going to look at each. Let's look at the top and let's look at the top right now. On the top of this, so we're going to break this into E times the area of the top times cosine theta plus E times the integral of the bottom times cosine theta plus integral of E times the sides times cosine theta. I'm just breaking it into its surfaces. We're going to look at each at a time. The top and the bottom are basically the same, but, look at the top. Which way is the area vector point on the top? You're going to shout this one out. I believe in you. Up. What's the angle between those? 0. Another thing that's important is the electric field is a constant everywhere in that top. How do you know that? If I slid that piece of paper around, you wouldn't have any clue. It would look the same to you. Any point that's that distance above it is basically identical. You can't tell the difference. It's like if you're flying over the desert, you can't tell if it's flat, but it probably won't be. All right, so this first term will be just E times the integral of dA top. Second term, we got to look at the bottom. Again, this is a bubble. You need a top and a bottom. You need both. You need both. And we can't have this bottom on the surface because the electric field is all sorts of wonky. It doesn't work. We got to put it down at the bottom. It actually makes our life easier. At the bottom, the electric field is down. For the same reason above it was up. Same exact logic. Which way is my area vector? Also down. Oh my gosh, it's the same exact thing. So we get E times the integral of the area on the bottom, because this is also 0 everywhere on that bottom. And E is a constant everywhere on that bottom. Fantastic. The sides, if we look at the sides and I draw the electric field on the side, there's the electric field on the side, it still points up. Which way does the area vector point on that side? To the right. What's the angle between those? 90. What's cosine of 90? So we don't care about the sides. So this is almost the exact opposite of the last one. The last one we cared about the sides. It didn't care about the top and bottom. This one we don't care about the sides. We only care about the top and bottom. So this is really simple. The area of the top plus the area of the bottom. This is where you need to remember that there's the top and the bottom, and this is really simple as well. The area of the top is pi r squared. The area of the bottom is pi r squared. What is r? Whatever this random radius is that we chose. Just you make it whatever you want. Turns out it doesn't matter. We just call it r. Some random radius. You can make this cylinder as big or as skinny as you want, and it won't change the problem. You'll see when we actually solve it. So boom, there you go. That's for a cylinder. 2 pi r squared. Or that's for a plane. Last one you do is a sphere. And all I'm doing is showing you the shape and why the shape. So if you're like, I have no clue what happened here. Just remember you're going to draw a cylinder and you care about the tops and bottoms. When it comes to a plane of charge, cylinder, tops and bottoms. When it comes to a line, cylinder, only care about the sides. For a sphere, this one is kind of the nicest in some ways because it's intuitive. If we had a sphere of charge, and I'm not going to use that one because it's negatively charged and that just has some more complications I don't want to get into. So here I got a sphere of charge, uniformly distributed. What Gaussian surface? So and I want to find the electric field at some point out here. We're going to find it inside the sphere as well, but for now we're going to look outside it. I'm going to pick we'll just do this random point. Same thing. Which way is the electric field going to point at that point? I want you all to spend 20, 30 seconds thinking about it for yourself. All right, and the answer is up to the right. Why is it up to the right? If you pick some random charge over here, that's going to make an electric field that kind of points away from that. You have another one that's over here, symmetry, 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 symmetry. For every charge, there's another one on the other side that's going to kind of cancel it out. So the electric field is just going to point directly away from it. So what shape are we going to do to solve this integral? This one's really nice. Actually, again, this is the easiest one, so I'm glad I get to end with this one. We're going to draw a sphere. We're going to draw a sphere around this. And if you want to make it really look like a sphere, you could do that, whatever. If you want to get real fancy, I tend to just not bother with that. But do know it's a sphere, not a circle. These are three-dimensional shapes, sphere, not circle. Why do we draw a sphere? Which way is the area vector going to point at that point? The same exact way. Yay! And if we pick any single spot on the sphere, every single place the electric field points, which is always going to be away, the area vector also points away. Isn't that nice? Oh, look at that. So what's the angle between those two? 0. And the electric field is the same everywhere on the sphere. Why? Because if I spun the sphere, you couldn't tell. If you spun that sphere and you rotated and changed, you wouldn't be able to tell the difference. It's symmetric. It's the same everywhere kind of around it. So this one turns really nicely into E times the area of a sphere, dA. We still haven't integrated yet. dA sphere times cosine of theta. And in this case, theta is going to be 0. E is a constant. So the area of a sphere is going to be 4 pi r squared. That's just the area of a sphere. These are things you're going to want to have memorized. It's useful. If you want the volume of a sphere, it's 4/3 pi r cubed. Another useful one. We're going to end up using that in some places. Okay. So this is how we set up. These are the only 3 types of problems: line/rod, plane, and sphere. I've now taught you which shapes to choose. So you can see there's all the beautiful shapes. And then I'm going to show you a nice little summary slide real quick before we start solving problems. Because if you're like, how am I, this is a lot of information. How do I keep track of it all? Where's it at? It's at the very end. First step when solving these problems, draw the correct Gaussian shape. We just discussed what those were. Solve for E dot dA. If it's a line of charge, you do E times the rounded side of the cylinder. That's what we just showed. If you have a plane, E times the area of the 2 flat sides, the top and the bottom. I didn't call top and bottom because, top and bottom is relative. It could be left and right. If you want the sphere, it's E times the area of the sphere. So I just derived all of those. Now we're going to start solving problems, and we're going to do the Q enclosed as well. We're going to kind of start putting the pieces all together. But I had to show you all what shapes to draw, and also ideally help you understand why. They're not just randomly chosen. They're chosen to because they make the integral go away, and showing you why they make the integral go away. All right, so which one are we going to start with? Symmetry A. There you go. It's the problem that we did last class, or 2 classes ago. I have a rod of charge with a charge density given by lambda. Find the electric field some distance r away from it. 2 classes ago, we solved this doing an integral. And the integral when we set up the integral, I said we're not going to even solve the integral because it requires trig sub and a bunch of time, and I didn't want to spend the time on it. This problem is going to be done in 3 lines. No calculus needed. Same exact problem, but we're going to use Gauss's law and solve it in like 3 lines. So we're going to draw where we're finding the field. I'm actually going to move this thing up a bit because I need to draw a Gaussian shape. We're going to find the field at some point P that's a distance r away. And what are we solving for? E. That's the question. What is the electric field at that point? That's the goal. We could do this with Coulomb's law. I've already done it with Coulomb's law. Obviously, I'm not going to do that again. We're going to use Gauss's law. First step, we draw a picture, and we need to add a Gaussian surface to it. What bubble, what Gaussian surface do I draw around the line of charge? Cylinder. Fantastic! So we're going to draw a cylinder. I'm so glad. I was really happy with that. I was afraid it'd be more quiet. When everyone responds, that means people are generally pretty confident about it. Great, there's a cylinder, right? Yay, there it is. Okay? And so then we set up Gauss's law. We write the integral of E dot, we just write it first. Q enclosed over epsilon naught. That's Gauss's law. And that's what we're going to solve. So I'm going to move this to another slide to just make it easier, give me more space. I ran out of room. Okay, so this is what we're going to solve. Move this up here, move the rod up here. The picture takes up way more space than any of the math is going to. Move that down here. All right, so the way we do Gauss's law is 1 side at a time. 1 side at a time. So first we're going to do this left side. E dot dA. We already talked about this. We already went through the whole derivation. Remember, because we chose this cylinder, it's just going to be E times the area of the sides of that cylinder. We just went through all that. What is the area of the sides? E times 2 pi r L. That is the area of a side of a cylinder. If you're like, how did we come up with this? Really simple. Really quickly. A cylinder, the side of a cylinder is just a bunch of circles. So what's the length of one circle? 2 pi r multiplied by L. How many circles do I have? L circles. If one circle has a length of 2 pi r, just multiply it by L, and you derived the equation for the sides of a cylinder. That's where it comes from. If you're cool with one circle, you can do a bunch of them. So great, there's that. The other side. Now we're going to do the other side. Q enclosed over epsilon naught. How much charge is inside the cylinder? This cylinder is an infinite cylinder. Obviously, I drew the sides of it because I can't draw forever and ever and ever. This cylinder encloses the entire rod. It goes forever and ever and ever and ever and ever. So how much charge is enclosed? All of it. All of the charge is enclosed. Now, the problem didn't give me Q. The problem didn't tell me how much charge the cylinder had. It told me its charge density. But remember that charge density is charge over length. That is the definition of charge density for a 1D object. Rearrange that. Q equals lambda times L. So what does this side turn into? Lambda L over epsilon naught. How much charge do I have inside? All of it. How do I write that in terms of charge density? If I know, charge density is charge per length. That's what it represents. Charge per length. So if I want all the charge, multiply by length. That's the logic there. Just like mass. What is density? Mass per volume. If you want the total mass, multiply by volume. This is just 1D instead of 3D. Okay, put all the pieces together. Just set the two sides equal to each other. So, we take this piece, and we set them equal to each other. So E, 2 pi RL equals lambda L over epsilon naught. I just set them equal to each other. To make it, this lambda over L is Q enclosed over epsilon naught. This E 2 pi RL is the left side. They equal each other. So they equal each other. Rearrange it. Algebra. So E equals lambda L over 2 pi RL epsilon naught. L's cancel. Lambda over 2 pi R epsilon naught. That's the answer. That's the electric field away from an infinite line of charge. So I guess it depends. It's not many lines. I didn't have to do any calculus. It was all algebra. So if we had solved the integral that I taught you all 2 classes ago, this is the solution to that integral. If you want to do it yourself, feel free to prove that to yourself. I didn't spend the time on it. So this is Gauss's law. It's convenient. It's useful. It lets us solve things we otherwise could not or would not want to solve.
What's an L? Like a lambda?
Yeah, there was 2 L's. There was an L to get the area, and there was an L to get the charge. Now this is an infinite rod, so it'd be really bad if we left L in there, because L would be infinity, but it cancels. So we don't worry about it. It's a beautiful thing with this. This ends up happening.
Oh, it's crossed out. Okay.
Yeah, it's crossed out.
Okay.
All right. So, this is the same thing, just in words. Same thing in words. Okay. Yeah, let's do this one, because this is going to build on this. I'm not going to do part A. So, I'll quickly set it up. Part A, I'm going to be like, we already did it. So, I'm not going to spend the time on it. A long silver rod. Oh, this is boring. Okay, never mind. We're going to do this and we make a really quick point. I'm actually not going to solve this. This one is, you just get the equation that we just derived. You should try to derive this yourself. You're going to need to. So part A, boom, just plug in the numbers. This problem, I'll draw the picture for you all. A long silver rod with radius of 3 centimeters. Oh, it's a solid rod. This is 3 centimeters, so we're going to call that capital R equals 3e minus 2 meters. Has a charge of, and this is actually charge density. Notice the units for this. Coulombs per centimeter, charge per length. That's charge density. So it has a charge density of 5. It's technically negative, not a huge deal. E to the minus 6, actually you got to be super careful here. You got to double convert this unit. So negative 5 microcoulomb per centimeter is going to be negative 5. I'm going to multiply it times 10 to the minus 6 to convert that e minus 6. And then I'm going to multiply it by e to the positive 2 to get rid of that centimeter, to get that centimeter to meter. This is just good unit conversion practice. So this is going to be e minus 6 e2. So this just comes out to negative 5 e minus 4 coulombs per meter. Good exercise for y'all. Make sure you do it. Don't just look at the slide and get the answer. Find the electric field at a point 5 centimeters away. 5 centimeters away is outside of it. 5 centimeters away is out here. How are you going to solve this problem? Draw the Gaussian surface, derive this equation, and then you just plug in the numbers. This one you just plug in the numbers. Okay. Part B. I'm going to give you all a minute to come up with the answer. See if you all can figure out the answer to part B. It says, find the electric field at some distance 2 centimeters from the center of the rod, an inside point. We'll call this like point 2. We'll call the other one point 1, just to separate them. If you are doing math, you're doing it wrong.
And Farad has three. Yeah.
All right, what's this rod made of? What material is this rod made of? Silver. What is silver? A conductor. What is the electric field inside a conductor? 0. The answer here does not involve any math. It requires you to realize this is a conductor. Yeah. Oh gosh, no. I will tell you, I assume you all know metals are conductors. I do expect that. Otherwise, I'll tell you if it's an insulator, I'll just say insulator. I'm not going to say like plastic or wood or things like that. That would be reasonable to assume you know it's an insulator. But just to make our life easier, I might put metal. I might call it a silver, aluminum, gold, whatever. I might call it a metal and assume that you can realize it's a conductor. That I will do. Insulators, I'll just say insulator. Insulators, I'm not going to go crazy and say like a polyethylene tube or some nonsense. Yeah.
So, assuming you don't say insulator.
Oh, that's a good question. I will tell you. Yep. Generally, if I don't say anything, assume it's an insulator. Actually, it goes the other way if I don't say anything. But honestly, I will try to do a good job of telling you all. On the test, if I have a problem like this, I will make it clear. And also what I often do on this, I'm a little kind this way. I'll often underline the word that it's silver or insulating on a test or things like that. Same thing when on a test there's positive and negative charges. If I say a proton versus an electron, I tend to underline that word because I don't want you to miss the question because you skated over it too quickly. It is important to have detailed reading comprehension and things like that. But I tend to not be too nitpicky on that. So silver is a conductor, E is 0 inside a conductor. If this was an insulator, this would not be true. If this was an insulator, we'd have to derive it. And we are going to do that. I am going to show you how to do that, but this is just a quick reminder. This one, you don't have to. But we will do some where you do. All right? You'll see it when we see it. All right. Let's do one or two more quick. I've already asked this, but let's see if it made sense. Given an infinite uniform plane of charge, what is the direction of the electric field at point P? Some random spot above it. Is it up, down, bottom right, bottom left? Or sorry, up, down, bottom right, up, left. Thanks. All right, 20 more seconds. Yeah. Epsilon naught? It's a constant. It's just, so it's 8, it's just like K is 9 times 10 to the 9. Epsilon naught is 8.854 times 10 to the minus 12. Yeah. It's a good question. It'll be, you're going to have to plug it in at sometimes. All right. In 5, 4, 3, 2, 1. Fantastic. All right. We already answered this. It's up. I already went through all the logic, so I'm not going to explain it again. Symmetry. Yay. Good. Okay. So now we're going to do it. Find the electric field some distance d away from an infinite plane of charge with a charge density of sigma. So we're solving for the electric field at some random point above the surface, some distance d away. So E equals question mark. You know, that's always what we're doing, right? In these problems, E equals question mark. What's the electric field at this point? This is a really important problem, and I'm going to explain why after we solve it. It's a really interesting one. So we're going to draw a Gaussian surface. You tell me, what shape is it? Cylinder! It's a cylinder, and in this case it goes through the thing, and then it kind of, juts out the bottom. You need to get good at drawing three-dimensional shapes. Look, if I can do it, you can do it. I'm not an artist. They're not too hard to draw. Curved lines, straight lines, not too bad. Okay, so integral of E, classic. E dot dA equals Q enclosed over epsilon naught. We're going to do the left side first, because it's on the left. We talked about this for a cylinder. We only care about the top and bottom. We only care about the area of the top and the area of the bottom. The sides canceled out. The top and the bottom we kept. So that equals E times area of the top, area of the bottom. What's the area of a circle? Pi r squared. Fantastic, fantastic. Pi r squared plus pi r squared. This R is some random radius that we put there. What's the radius? It's the radius of this thing. It is not the distance. It's not d. It's the radius of our bubble. So we get E times 2 pi r squared. Okay, looking at the other side. How much charge do I have inside of this bubble? I do not have all of it. Clearly this bubble does not include the entire plane. That's not a crazy claim. How much does this bubble include? It includes that much charge. How much charge is that? So this is my Q enclosed. What does my Q enclosed equal? Remember y'all the definition of charge density. Charge density is Q over area. In the 2D one, instead of length, it's area. Okay, so rearrange that. Q equals sigma times area. What's the area of the circle? Pi r squared. It's the same cylinder, it's just a different circle in that cylinder. So that turns this Q enclosed becomes sigma pi r squared over epsilon naught. One last step and then we're done. Set them equal to each other. So E times 2 pi r squared equals sigma pi r squared over epsilon naught. Solve for E. What happens to the pi? It cancels. What happens to the r squared? It cancels. What are you left with? Sigma over 2 epsilon naught. That's the electric field to an infinite plane. And there is something very, 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 very important here. Do you all see D in this equation? The distance doesn't matter. The electric field from an infinite plane is the same everywhere. 10 meters away from it, it's this value. 5 meters away from it, it's the same value. 2 meters away from it, it's the same value. The only thing that matters is how your charge is spread out. It's a really weird problem where the electric field doesn't get stronger when you get closer, and it doesn't get weaker when you get far away. It's the same everywhere. It's a weird thing, and this is the foundation of capacitors. Capacitors are two of these put together. If you've heard the word capacitor. So yeah, we'll talk about this more in the future. But that's the main point here. We're doing pretty good. All right. Have a good one, y'all. See you on the other side. Practice things.